Hey everyone, welcome back to The Explainer. Today we're stepping right into phase 2 of our series. Putting on our senior planning engineer hats, we are looking at generator and transformer modeling, specifically synchronous generator reactances. And we're tackling a massive, incredibly dangerous misconception. It's a misunderstanding that can literally cause electrical equipment to just explode right in front of you. And that is treating a synchronous generator as a single, fixed impedance during a short circuit. Spoiler alert, it's absolutely not. You see, the instant a fault hits a generator, the fault current doesn't behave like a simple resistor circuit at all. No way. It's a highly dynamic, really violent event. When that short circuit occurs, the current slams to this massive peak. But it doesn't just hang out there. It actually decays in 3 distinct, predictable stages over the next several seconds. So here's how this whole thing breaks down. First, you get that instantaneous massive current spike. Then we hit stage 1, the sub-transient decay, which is the absolute steepest drop. After a few cycles, we transition right into stage 2, the transient decay, which is a much slower, more gradual decline. And finally, in stage 3, the machine settles down into its steady state. If you try to model a generator as one fixed impedance without accounting for these specific time-based decay rates, well, every single one of your fault studies is going to be wrong.
Okay, so why does this happen? Well, it actually starts with the physical geometry of the machine itself. Think about our 2 main types of rotors. Cylindrical rotor generators, these are the ones usually driven by high-speed steam or gas turbines. They have a perfectly smooth, uniform air gap. Because of that beautiful symmetry, their magnetic reluctance is uniform, meaning their reactance is exactly the same in every direction. We say their direct axis reactance, XD, equals their quadrature axis reactance, XQ. But salient pole generators, which you'll typically find on slower hydro units, have physically protruding poles. This physical difference creates a different magnetic reluctance, and therefore different reactance, along the pole axis compared to the space between the poles. So in this case, XD absolutely does not equal XQ. When you look at the cross-section of an elementary 2-pole machine, you can physically see it. The direct axis aligns perfectly with the poles, and the quadrature axis sits right there between them. This geometric difference fundamentally changes how each machine type responds to magnetic disturbances and faults. We're not just talking about abstract math on a page here. It is physical steel and copper dictating the flow of massive amounts of energy. So let's look at how this physical geometry translates into the temporal reality of a fault. We call this time-based decay the AC decrement. In the very first few cycles after a short circuit, the machine's internal magnetic flux just cannot change momentarily, right? So it presents its absolute lowest impedance, known as a sub-transient reactance, or X''D. Over the next several cycles, as the damper windings decay out, that impedance rises to the transient reactance, X''D. And finally, after several seconds, the field itself settles, leaving us with the steady-state synchronous reactance, just plain old XD. So here is the absolute crucial mathematical progression you need to memorize as a planning engineer. Sub-transient reactance is less than transient reactance, which is less than synchronous reactance. It's that simple. Because of Ohm's law, as time passes after a fault, the generator's internal impedance is increasing, which means the AC fault current is decreasing from that massive initial spike down to a lower, steady value.
All right, let's put this into practice. When life-or-death hardware decisions are on the line, say you're specifying a multi-million-dollar circuit breaker to protect a generating station, which of these 3 reactances do you actually use to safely size that breaker's interrupting capability? Take a quick second and think about it. Well, if you said sub-transient reactance X''D, you hit the nail right on the head. You absolutely must use the sub-transient reactance because it defines the absolute lowest impedance the machine will ever present, and that dictates the massive worst-case peak current. And think about it, when is the breaker asked to operate? Right there in those first few cycles. If you use the steady-state synchronous reactance, XT, instead, you'd vastly underestimate the current. You would effectively undersize every single breaker on your system, which practically guarantees a catastrophic failure when a fault actually hits. But hold on, the plot thickens. Layered right on top of that AC decrement we just talked about is a completely separate phenomenon called the DC decrement. You see, when a fault strikes at a random point on the voltage wave, inductance actually forces the current to start exactly where it was pre-fault. To bridge that gap, a decaying DC offset is generated, and it pushes the total fault current completely off-center, making it highly asymmetrical. So how fast does that DC offset fade away? Well, that depends entirely on the circuit's reactance to resistance ratio, or the X/R ratio. Near massive generators, you have very little resistance but huge reactance, so a high X/R ratio.
meaning a really slow DC decay and a wildly lopsided fault current. But way out on a distribution feeder, resistance is higher, X over R is low, and that DC offset dies out almost instantly, leaving you with a nice symmetrical wave. And this isn't just theoretical, guys. It's literally codified into the standards. As the source material points out, if your system's X over R ratio is greater than 15, which, by the way, is incredibly common near large generating plants, that DC offset lingers for so long that the actual peak current the breaker must interrupt is significantly higher than just the symmetric AC calculation alone. You actually have to apply an asymmetry multiplying factor to correct your calculated fault current. That ensures your breaker doesn't just melt under the combined stress of the AC sub-transient current and that lingering DC offset. This whole dynamic is exactly why sizing a breaker requires two distinct separate ratings. First up, you have the momentary, or close and latch rating. This covers the very first cycle. The breaker has to physically withstand that massive asymmetric peak, which is heavily influenced by the high X over R ratio and the X double prime D sub-transient reactance. Second, you have the interrupting rating. This applies a few cycles later when the breaker contacts actually pull apart. By then, the DC offset has partially decayed, and we're looking at a value much closer to the symmetrical RMS current. Honestly, confusing these two ratings is a fatal error in substation design. So let's bring this all together. You might have come into this explainer viewing a generator as a single, static box of fixed impedance, but now you can see fault analysis for what it truly is, a totally dynamic, multi-layered process. Step 1. You map out the machine's geometric AC decrement, tracking how X double prime D rises to XD. Step 2, you calculate the network's DC offset based on the specific X over R ratio at the fault location. And finally, Step 3, you apply the correct asymmetry multiplying factors to make absolutely sure your hardware can survive the absolute worst-case scenario. Okay, so we've successfully mapped the spinning, dynamic chaos of the synchronous generator. But generators only create the power, right? It's the transformers that step it up and move it hundreds of miles across the grid. So here's a question to leave you with. If the generator's model changes based on time and physical geometry, how on earth do we model the silent, static equivalent circuit hiding inside the massive steel tank of a power transformer? Well, in part 2 of this explainer, we're going to crack open that steel tank and see exactly what's happening inside. You definitely won't want to miss it.